Okay, so um, I was not able to take the last class. Uh, I heard that you guys have a problem with the code of that Hoffman coding. I get that it's a very long code actually, and it's very hard to understand if you don't follow. Uh, I mean, it's actually the structure is also very complicated. So I will discuss the same problem, the Hoffman coding today, and its code. And I am switching to C++. I think most of you are requesting since a long time, and Sir told me to switch to the to C++. So today I will do the same coding in C++. It's almost similar code. Uh, there is like basically no difference between yeah, C++. There is just a little bit syntax difference, but the structure wise it's almost same. The same code that we have done in C, just a little bit uh, like different in the syntax. Okay, so I think you guys probably have the problem with the heap that I have used in there, and probably have questions like why we are using these heaps and how we are implementing that code. So I think I'll first discussed a little bit about this structure of that Hoffman code, like how we have uh, come up with this coding, and then we will move to the coding part. Okay, and if the time permits, if it doesn't, then we will do it in the next class in tomorrow's class. Okay, so uh, before going there, before starting, uh, I want to know that have you guys gone through that code, like some of you or any one of you, or and try to understand, like you if you have any questions regarding that. Uh, First, I want to know that. Then I will move on to the discussion. Okay, so if there is no queries, then I'm starting. Mm, I think it's allowed. Please check.
It's any level. Thank you, sir.
Okay, so uh, just before starting, I will give you guys a short recap of this Hoffman code and how we are building this Hoffman code. Mm, So Like anybody recall? It's actually a my screen is not visible, right? Right.
Yes, sir.
Okay, okay. Okay. Yeah, so it's fine.
Yes, sir.
Seems visible, right? Okay, so let's start. Okay, so uh, just a short recap of what we were going to do. Uh, oh, yes, right. I also have a query. Like, have you guys have any questions regarding uh, this or this dynamic memory allocation that we have used in our coding, C++, coding in C actually? We will use the same function in here also. Uh, I have I have this query, like, do you have any questions regarding this malloc or calloc, use of this malloc or calloc, how we are using it, or like why we are using it, or anything like that? Do you have any query like that?
Sir, if you don't mind, could you recap once more it, malloc and calloc?
Okay,
Just sort
so
of it.
yeah, so okay, uh, malloc and calloc is basically the dynamic memory allocation. Uh, before malloc and calloc also, like pointer is okay for everyone, I guess, right? You guys don't have any questions regarding this pointer, I hope. Is pointer fine for everyone? So
Yes, sir.
if you have, yeah, any question? Okay. So if pointer is fine, then I'm going moving back to this dynamic memory allocation. This dynamic memory, sorry, dynamic memory allocation. Okay. So I'm starting with this one today because we'll need the same function uh, while we will define the heaps again, like we did in the last class. Uh, it's same in C++ as well as in C. So what happens is that when you declare an array, what happens? Like if I declare an array, integer type or any type, let's say integer type for this integer a some size of an array, right? Um, okay, so if you have when we declare this, what does it do? It creates a, like, your memory is a kind of a block of consists of these blocks, bits called bits, and it allocates some space in the consecutive spaces uh, corresponding to this size, that number of spaces it blocks for these integer values. Okay, so this is an array that we have defined. Now it has a fixed size, so we know that what would be the length. Okay, and it's defined uh, like in the beginning. So you know that this many spaces we need, and we will allocate and the program will allocate this many integers in there. Okay, but the problem is that uh, like if we are not sure about the about that we don't want to allocate it like in the beginning. We want to allocate it like when we are using it, and then we want to let it go, like free the memory. Okay, so we don't want to store the values in that particular space for a long time. Okay, we want to store it for certain when we are operating on it, and then we want that space to be free. Okay, so that's the dynamic memory allocation. So there are two things. One is static memory allocation, one is dynamic memory. So if you look at this type of things, this array, or like, yeah, I mean, array is a good example. So if you are thinking about this array, so the memory that you have defined in the initial, initially, whatever you have given the size of that array, the memory, that many spaces, I mean, during your whole programming, whatever code you write, like if your program is this one, okay, so whatever code you run, this is, if this part is your code, throughout this code, this many space, like this array size space will be blocked, okay, in the memory. Okay, but like we want to, we don't want to block the memory with this type of fixed sizes, fixed size in the memory since the beginning. We just want it like when we are using this, then we want to put, we want to allocate some memory, and after using, after when we use this space, we want to like leave this space free. Okay, any vacant to be ready to allocate more memories. Okay, or something you can allocate someone else, something else in there. So this is the dynamic memory allocation. Okay, and this is actually there are parts in the memory. I mean, also there are a lot of things. So this memory has this called heap, and there is another thing called stack. Okay, so in like this array type, all these allocations, these are done in the stack. So we and this dynamic memory allocation that we do in here is actually done in the part called heap. Okay. Uh, so the benefit of this one is that we can use it like it actually gives you a better access, better manipulation of the memory, and it's also like allow you to use the memory whenever you need to. Okay, so it's a bit efficient structure compared to the static memory. And if you know that since we are working with pointers, pointers actually give you access to the value stored at some address. Okay, so basically it's a pointer. Okay, we are manipulating all these things through the pointers. And the structure of this one is done by this malloc and calloc and these two functions. Uh, so what is dynamic memory allocation? I think it's fine now, or any doubt? And like we can directly manipulate these entries in the memory itself. Okay. And also, like, you know that when you are defining an array, your size is fixed in the beginning. But like in here, it's actually depending on the number of entries. So it's basically actually depending on the number of entries. So you are not bound the size in the beginning. while you are allocating the dynamic programming, dynamic memory allocation, your size is not finite. It's depending on the number of entries. So if like if you are entering 5 elements, it will allocate 5. If you are entering 6, it will allocate 6. But if you are defining a size in the beginning, like what we did in array, we have a size in the beginning. So that many space you have to specify in the beginning. Like if you want to alter it, then you have to also either have to define a different array, or you have to change the variable. Like if you are defining it by a name of the variable, like here size, if you have to define size equal to 5, size equal to 6 for every time whenever you are using it. But this and also like that will create an ambiguity, because if you are defining 5, 6, if you are changing the sizes, the memory will contain that many numbers in there. So you cannot like change this array. Like what I am saying is that if you have A5, okay, so not A5, it's wrong actually. Array of size 5, let's say. So if you have this array of size 5, what will happen is that I'm writing A5, but okay, 2, 3, 4, 1, 2, 3, 4, 5. Yeah, so there is these 5 blocks. If you call A4, this will just take up to this space, na? Because these are stored already in the memory. Okay, so there is no flexibility that this will represent something different, like 4 blocks of memory. It's representing on the same array. Okay, but here you can operate directly, like if you are defining with respect to this dynamic memory allocation, like using malloc or calloc, then you can directly, like it's depending on number of entries that you will give in your arrays. I mean uh, this dynamic arrays actually, we can say, but let's not say that right now. We can say, yeah, dynamic array, you can say that. But okay, so there the size is not fixed. So within the same name, you can enter 5 elements, and after using that, you can free the space. You define another. You can take another 4 elements in there, and that would be a new array. You can use the same thing as I mean, you can use the same name, but the entries could be different. There is no problem with that. Okay, so this is the benefits of this dynamic memory allocation. And like what is malloc and what is calloc is two functions. Dynamic memory done by one is malloc and another one is calloc. So what is the use of this malloc and how we are using it? I'm going to discuss it now. But before that, just what is the dynamic memory allocation? Is it clear? Like why we are using it and how it's affecting? Is it is there any problem with my voice? Is there any problem with my voice? Have you like did not? It's not only reduce time complexity, it actually helps you to access better access of memory actually, because see, like in array, like if you are using one array to define, let's say at a time you are using, let's say, uh, 10 spaces, okay, array of size 10, if you think about that one. So you cannot manipulate it, like if you are using it in a function. So whenever you store a value inside of that array, it's fixed. That block of memory contains those values, and these are fixed. Okay. Whatever alteration you do in there, and whatever program you compute, after that the size is fixed and the values are fixed in there. after whatever your function executes, you call an array inside a function, and the function runs, and it assigns some values inside the array. Okay, those values stays in there. So if there is another function or that are using this one, or you call that function again, those values are stored inside that array again. Okay, so you have to like, you cannot use the same thing twice in there, or like repeatedly. Here the benefit is that after using one time, you are releasing the memory. So there is nothing inside the memory. You have used it like for your purpose, and then you leave the memory free. Now, when you are using it again, it can take like uh, different inputs easily and not bound on the size. Like in there, you have to use like 10 times every. The size should be 10 if you are defining an array of size 10. But here you can use, for example, like for one case you can use 8, one case you can use 9, one case you can use 10 number of inputs. That doesn't matter. Okay. So that's the difference. So that's the benefit of using this dynamic memory allocation. Okay. So now this functions. So what is this malloc and so let me. Okay, I will describe this context of malloc now in C++ settings, not in C. But like it's similar type. So it's, so, so the syntax is it's actually a function. So how we uh, write this function is that it's the name of the pointer. So for example, it would be the like whatever integer, if it is integer PTR, if you are naming it PTR, it's PTR, whatever name you want. So the syntax is that it's the pointer name, and then we write the type of the variable, that whether it's an integer or a character or some other data type, if you whatever you are using, and this malloc of size of that data type actually. So size of that means like if you, I think you know that integer has this 4 byte, uh, right? Integer has this 4 byte character. I don't know. Character. I think character take 1 byte. So this type of that size we are talking about. Okay. So this is the syntax of using malloc. Uh, so what it does is that it uh, it actually, when you are defining it in this way, so depending on this type of the I mean data type, whatever type you are using, it asks, it actually allocates some memory, like some bytes in there, and when you call this function, this actually returns a pointer to the first byte of that allocated memory. So it allocates some memory in there, some memory in there. So whenever you call this malloc, it actually returns a pointer to this space. Okay. And of course, it has these properties that it allocates dynamically on its runtime. So this is it. So this is how we define the malloc. Uh, one example is that you can, like, if you are defining an integer, so if your name, this is the name of the variable, the pointer, and then you are using, let's say, integer. We are mainly using this type, but I think we also use structure. I don't know whether we have used structure. I think there are also structure variable that we have used in the last coding. So it could be any type of variable. Huh? So integer star. It's I'm writing the same thing based on the integer, and this malloc of this size of integer. Okay. So this is how we define malloc. Hmm. So what does it return? It actually the type of this function is actually it's a void. Okay. Uh, so if your allocation like if the size is 0, uh, then it's actually depending on the library of implementation that whether it will return a null pointer or not. Uh, and it, it's like if you see an example of how it works, I will okay. I will do one code before starting the Hopline code. I will show you one example of how this works really, but it's same. I think I have done this before. So also like after using malloc, you have to like also whenever you are done with this like uh, let's say you define an uh, block of memory like an array. You can think of it as an array actually, where the size is not fixed. So when you define this one, then you have to also after using this one, you have to like deallocate all this memory that we do using free. Okay, using this free function that will deallocate the memory that are allocated by this malloc. Okay. Uh, so I think like how malloc works or what is the use of malloc? Is it okay for everyone or any question? Chapter one, yeah. I mean, no. So the size is that one actually. This beats that we are talking about. Okay. So any questions? Any questions? Explain. Oh, okay. Oh, yeah, between malloc and calloc, I mean, the difference between malloc and calloc, like why we are using calloc. I would come to alloc. Alloc. Uh, Basically, what happens is that when you are using this malloc, I am not uh, like initialize anything inside. Initialization means like whenever you are using an array, let's say, suppose you are operating on an array, and you have this numbers in there, and like in the beginning you set a value for these spaces, like this value is 0, this value is 1, this value is 0, 1 or 0, something like that. So this is the initialization. Like before your coding, you have given some value like before you start, you have given some value allocated to these spaces. Okay. So that's the initialization. So you have initialized some values in there. But what malloc does is that it just allocates spaces. It doesn't allocate any values inside those spaces. What calloc does is that it allocates 0, basically 0, to every allocated space. Like calloc is same. Calloc is same as malloc. In terms of using, I mean, it represents also a dynamic memory allocation. It also like initializes at the beginning, and it's also give you a like block of memories. What there is some extra purpose served by this calloc is that it allocates 0. I mean, it initializes 0 to every space of that allocated memory. Okay, so whenever you call a calloc or something, or whenever you call calloc, it actually what does it do is that it actually allocates some block of memory depending on how many entries you want, and it initializes 0 everywhere, wherever you want. Like how many entries? If you are looking for like 5 or 6 blocks, all of them will be allocated 0. All of them. Okay. So that's the difference. Like there is a 0 allocation, one argument malloc, and two argument calloc. Where is this one? What do you find? I mean, I don't get what do you want to say. What do you want to mean by this one argument malloc and two argument calloc? Are you talking about okay? I guess you are talking about the defining of this calloc. Are you talking about this? Oh, okay. So comma. You are talking about this. Okay. So I get it. So you are talking about the functions, right? So how this 5 comma, I mean, let's say a comma size of integer for calloc. And so malloc and calloc is this one that is some whatever one is size, another one is a number. That number is depending on like how many spaces you want. Uh, so you are talking about this, I guess, right? Yes, yes. So this one is two argument means it's yeah. Mm, so so your question is why it has two arguments. So it's actually see this stores the same number of values. Like if you want, like if you are defining defining some spaces using calloc or using malloc, uh, uh, the same number of space can be defined by calloc also. But the extra thing is that the zeros, the initialization of zeros. Okay. Uh, Also, like why? I mean, why it has two arguments? It's actually the structure of the function, but I'm not sure about the answer. Cannot be- But I know the meaning of these two arguments. One is the size of the integer that we have used, and another one is the number of spaces you want to allocate for that uh, part. So I think it's basically the syntax of like how they are defined. Oh, the difference is the initialization. The difference is the initialization. When you use, if you use malloc, there will be no values stored inside those spaces. And if you are using calloc, there would be like 0 stored in there. So if you call that array and you are using it, suppose you define not array. I mean, suppose you define that dynamic array. I can say that dynamic array. So if you are using that dynamic array as a like if you call them whenever if you define it using calloc and you call that array, then that what will happen is that that array will contain zeros. Okay. Whereas if you define the same array using malloc, it will contain nothing inside. Whatever input you will give, it will take that off. Okay. But for calloc, you have to that manipulate that 0 entries. Okay. So that's the difference. And the basic, like why they have two arguments, it's basically the structure of the functions, like how they are defined. Uh, the arguments of the function of calloc is one, the size that we have used for the size of the data type, and another one is the number of spaces we want to allocate for that. I mean number of spaces we want to allocate. These are the two arguments for calloc. And for malloc, it's directly like number of the size of the bits multiplied by the number of spaces it wants to allocate. So that's the structure. It's just the structure. Okay. So it's a very good question. Actually, I don't know how these functions are defined, like what are inside this malloc and calloc function. Like the code of malloc, if you can say, like which one defining the malloc. Uh, but what I think is that these functions are basically we are using it like user defined, um, not user defined. I mean they are predefined functions. We are using it directly, but I think that it's based on how they are configured. Okay, the two arguments and the single argument. I mean, maybe it has something to do with the initialization also, because whenever you are calling calloc, it also initializes the values. So I guess it has to do something with the initialization. I think. So that's why we are using the number of integers and number of and the size of the number of integers, not number of spaces that we need, and the size of the data type separately. Whereas for malloc, we are directly just allocating the number of bits by multiplying the size. It's easy to see that in malloc. In malloc, basically, when we use malloc, if you are defining some, it's a single pointer now. But if you are defining some other thing like array type thing where you need to define some spaces like 5, 6 spaces, so it basically goes like this one: integer star array, uh, integer star malloc array, size of array. I mean, let's say your size is 10, so 10 star size of int. So we define it in this way whenever we are using malloc. Okay, so this is basically what it actually, size of integer means bits. So that many bits. These actually defining the size of bits that you need to store those values. So it just creates that many spaces in the memory. Whereas when you are using calloc, you just use like, if you are defining the same thing using calloc, you just do this calloc uh, 10 comma size of int. So this one is the same thing, just having zeros inside. Okay. So these are the two main differences between calloc and malloc. And obviously, after using every time, whenever you use malloc and whenever you use calloc, you have to deallocate that memory also. Yes. So that will so for this purpose you will use the we use the free function. Okay. So after using malloc, you have to deallocate that space. Otherwise, there would be error. So dereferencing also important. Deallocation, sorry, not dereferencing. Deallocation is also important as well as like allocating. So this is the structure of using malloc and calloc. Okay. So this dynamic memory, that's not dynamic, yeah, dynamic memory allocation that uh, we have gone through, same as C, it's same in C and C++. Okay. So we now move to this Hoffman code part. Okay. Uh, I guess any other question from this dynamic memory allocation? Okay. So if not, then I'm moving to the heap. Next, I have used in the last class. I mean, in the last tutorial, we have came across this heap structure. I know that it's not covered in your class, but you guys say that you have done it before. So I'm just revising heap once again. So it's a data structure that we use to actually implement in a lot of things. Actually, it can be used in sorting, and also it can be used in this priority queues. Have you heard about priority queues? Priority queues. Okay, so it's another important structure actually. These priority queues are uh, means not clear. I mean, in priority queue, what is mean? There is no mean in priority queue. Um, although, I mean, I don't know where mean comes from. Uh, but oh, okay. What priority queue means? What does priority queue mean? Okay, so it actually represents the like it's kind of like, have you heard? So you know heap, right? So what do you do in heap? So there are two kinds of heaps, right? One is a max heap, another one is a mean heap. So the heap is actually a binary tree. So binary tree means it has like every node has at most two children, and it's actually a complete binary tree. So complete binary tree means complete binary trees are like, so is it a complete binary tree? So it's not, right? Because in complete binary tree, it should be, yeah, the left child should be present before the right. So this is the, now this is a complete binary tree. So is it, is it a complete binary tree? Okay, let's see. This one now. It's not complete binary tree. Okay. So how can we make it complete binary tree? Every node has two child. So what about the leaves? So except for leaf, every node has two childs. That's the definition of complete binary tree. Yes, this is complete. Right. Complete does not mean that every non-leaf node has two children. Okay. It means that if you are visiting at some level, okay, every child has, except for the last level, actually, every child has two children. Okay. And like, if it has, like, for example, okay, so this is complete, the one is right. Yeah. So it doesn't, so complete binary tree means that except for the last level, it's completely filled, like everything is filled up to that level. Above last, I mean this one, up to this one, everything is filled. Every node has two children up to this one. That rule is applicable up to this one. Okay. After that, you are filling this one like from left to right. Okay. So this is complete. And so does this one also. Okay. So you are filling it from the left in the last level. Okay. So is it clear? So this is complete binary tree. Okay. This is also a complete binary tree. Okay. It's not that every node has to have two children. Every node has to have two children. It's applicable up to the level, the highest level -1. Okay. Fine. So our heap is a complete binary tree. And it demonstrates a property. So there is the thing called min heap, and there is a thing called max heap. So we actually use min heap. If you recall the last Hoffman coding. So this min heap actually how it looks like is that it has the root as the minimum value. So min heap means that you have some numbers. Let's say you have an array of numbers. Okay. So this root contains the minimum, and its two children has the property that they are like bigger than this root. Okay. Also, if it has children, it has to satisfy that same property, that the value of these children would be bigger than this node. Okay. So it's a structure like this one. So for example, like if you have two, let's say this 2, 3, 7. Yeah. Yes. SNR. So this is kind of this one. Okay. So where the root is corresponding to the minimum. Its root is always smaller than the children. So its complement is the max heap, is where the root will represent the maximum value and the children would have the minimum values. Okay. So this is that min heap structure that we have used. But you can see that, like, if you insert something inside this array, then you have to adjust the whole. You cannot just put that value like anywhere. Okay. If you recall that it should be a complete binary tree. So if I add anything, it should go in this place. Okay. But that also has to satisfy the property that it should be greater than 7 and greater than 2. So these adjustments, like sometimes we have to adjust these nodes from like whenever we are inserting. So there are these operations, like insert, like same thing. Like if you have you done like, oh, I think no data structure is covered in your class. No? Oh, so have you heard about these stacks queues? Like, do you know, like stack queue, linked list? Have you heard about it? Yeah. So what do we do in stack queue or linked list is that we add some, we can insert some elements, we can delete some elements, we can like, we can also search. These three operations are there, na? Insertion, deletion, and search. Uh, Deletion means in stack, you can say it like pop. In queue, we use the deletion or dequeue. And in linked list also, we can delete, add, insert anywhere in the linked list, or we can search in the linked list. So these operations, if heap is also a data structure, it's like a binary tree. So I think you also have done the binary tree. So binary tree itself for data structure. But the difference between binary tree and this one is that it also has this property of this ordering property in here, that the root should represent either the maximum or the minimum element of that array, and so on and so forth, maintaining that optimal that substructure everywhere. Like whenever you are, if you are visiting a subtree also, every node, like every parent should be smaller than the children. Okay, that structure is preserved everywhere throughout the tree. That's your heap tree, you can call heap tree. Okay, so this process, like whenever you are entering a new element in there, you have to modify that heap, because you cannot put it anywhere. Because you have to maintain the uh, certain conditions, that it has to be a complete binary tree, it has to be a uh, has to satisfy this heap property, that either it's I mean, its parent should be smaller than itself, than the value that are going to be inserted. So keeping all these things in mind, your there is a function actually, this called ep5, that we have used in the last class. Uh, so this ep5 is used to 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 maintain the balance. Okay, to the purpose of ep5 is to create, like whenever you are inserting some element in there or you are deleting some element in there, ep5 will modify, will change these trees. I mean, change these roots. Like if you are inserting some value which are smaller than 7, okay, then you know that 7 cannot be here, because the element should come here. So we have to like put that element in here and bring 7 down to this place. Yes, I will. Okay, okay. So like I was talking about the operations, insertion in heap and deletion in heap. these two operations. So suppose you want to insert, so this array that we have, if you represent it in an array, what are the elements we have? 2, 3. I'm writing it in a sorted way, but 8, 9, 11. Okay. So let's say you enter 6 now. So now when 6 is inserted in here, I have to put 6 somewhere in here, and the only position left for me to make it a heap is assigning it to this place. But this is wrong, right? It does not satisfy that property because the root is not smaller than 6. So what we have to do is that we have to adjust it. So we have to bring 6 in here and 7 down in here. Okay. We have to use this kind of modification. So this is done by this function, this kind of things is done by this function ep5. Okay. That whenever you are entering a new or you are inserting some new number in the heap, or you are deleting something, you have to, yes, you have to balance. Yeah, that function ep5 is a function. So you have to balance and make it a heap again. So that process is called ep5. Yeah. So and this heap, you can see that since we are kind of talking about ordering, it actually you can use it uh, for sorting purposes also. Okay, so this minimum is like finding the root. You know that the root corresponds to the minimum value, so you can extract the root. So here it's extracting. So there is an operation extract mean. I think you can find it in priority key. Okay, well, I will come to the priority queue, but first let me like how you can sort it. So there is a heap sort algorithm. I think you have heard it. So it basically use this heap repeatedly. It built a heap and extract the minimum, I mean the root, and then again run the heapify, take the root, run the heapify, take the root. Okay, so it goes like this. It's a very good sorting algorithm. I mean, although running time does not improve, but it's like it's still order n log n, but it's it's like using the heap structure. Okay, so every time it extracts the minimum, it takes the root out of the array, and it then rearrange and make that array another make another heap and take the minimum out. So every time it gets the minimum, so you just put it in another array, and you will get the sorted array. So this is the heap sort algorithm, and use of heap is this one, that this priority queue. So priority queue here, it's actually depends on, like, again, it's similarly like this one. Uh, Here we are giving priority to the minimum value. Okay, so that's the thing. Like in the priority queue, the root, I mean, you will implement the priority queue in a heap, and the priority queue is actually ordered in a way that whatever the thing that you are giving priority, it should come to in the beginning. Okay, so uh, if you are looking at the minimum value, so you just implement the min heap, you take the root out. Okay, and that's your prioritized element, and that's the structure corresponding to the heap. That's your priority queue. Okay, so this is but I mean, priority queue is not needed for this. Heap is fine for us. We can simply uh, cover the things that we need with the help of heap only. Okay, so let's focus on heaps only. Okay, heap, yeah, heap, heap structure, heap data structure, and heapify. Okay, so what is heap and what is heapify? It's just a rough review of this one. I mean, how we are using it, that is a different. Like, should I have to discuss like what is CP5, or it's fine? I'll just keep it. Okay. Okay. So how the CP5 works? Okay. So okay, I'll discuss CP5. So as I was saying that if you are inserting in, if you want to insert some element in this heap, it has to satisfy the properties, right? That it's a binary tree, as well as the root should be smaller than the leaf. So how we do that? So when you are inserting some element in there, we have to like modify. So this so so when we use hippie. So suppose note some note. Okay, so here where the property is violated, if you add 6 in here in this level, um, that's some note I, and the heap property is violated. Okay. So what it does is that it, as a purpose is known, that EP5 or let's use this term, fix the violation. So what are the steps for EP5? So what we do is that, see, so here the violation happened in the immediate node, but it could happen like there could be a long tree in here, rooted at here, and like this tree could be long, right? Very long, and there at some point if there is a violation. This is the node I that we are talking about. So if you have a tree, like this is a binary tree, so this tree could be very long tree, and your violation is at some point, some node here in I. Um, then let's see, it's just not the immediate violation. It could be like it could be the minimum element. Okay, so whatever you are entering, it could be the minimum element. So it has to traverse to the root, right? So there is a big part where things need to be uh, modified. Okay, so 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 now you can also think. I mean, you can also see that whenever, like wherever you are trying to enter this number I mean, obviously it will be on satisfying the binary tree property. So either you are adding it uh, as it like if as, and also it would be on the lower level. So whichever space is available. If there are like no children, so if you look at this one, let's say so up to so let's say you have this tree. And up to this, up to let's say up to this portion, it's completely filled. It's already filled. And now you are entering. So whenever you enter, so let's say if this one, the newly inserted node. So if it violates, like if you look at this node is your I, but the violation occurs, or you can consider this also as I. Doesn't matter. Anyway, it's same actually. So if there is violation in this place, and this could be the minimum number. So if the newly inserted is a minimum, is the minimum, then the violation actually goes up to this place, right? So you have to adjust a lot of things. It's not just you can change these two things. You have to change these, change these, change this. Okay, so basically what you have to do is that you have to carry the I up to the root, okay, by adjusting those values. So this is what the amplify does. Okay, so it will swap the values uh, recursively with the left side, and so what you do is that you will find the minimum actually. So you can see that we are what we are using. We are using the mean heap. Okay, so all we are interested, like whenever we are trying to swap with a parent and child, we have to find the minimum one. Okay, we want that minimum to be on the root. Okay, so let's say if it has a left child which is smaller than, no, it cannot have smaller than the root, so then the heap structure is already violated. So I have assumed that up to now it's already a heap. Uh, so we have to find a minimum in the root. Okay, and we have to check like wherever up to which the violation occurred. So and then we have to check that if there is like what is the minimum value among the left child or right child, and then we swap the values and correspondingly accordingly, and we update the tree like that. So if this is so it's a violation, so this one is smaller than this one obviously. So what we do is that we bring this one up, and then we check, okay, the value is smaller, still smaller. Okay, okay, update, we keep on doing that. That's your debug function does. Okay. So is it clear, or I mean, shall I take an example and execute it? Do you need an example, or it's fine? Like how we are it's just swapping. It's just swapping the elements, and like based on, okay. So I'm taking the same thing. but here the root is already minimum, so I don't have to go up to the, okay. I can take numbers. That's 3, 5. Yes, sir. So let's say this kind of numbers. Now insert 4 in this. So now it's a binary tree. Okay. So insert 4, the space for 4 is this one, right? This is the space I have to make it a binary tree, but it's not a correct place, right? It's violating the heap property because the root is bigger than this value, the children. There is the children. Okay. So what is the immediate process? We can swap these two. That will do no harm, right? So I will swap this 4 with this 10. Okay. Now again, it's a violation because this value is bigger than this one. That cannot be the case. So we have to swap once more. So 5. Now if you check the root, okay, it's fine because root is smaller. Okay. So there is no violation in that case. So we have done modifying this tree, and this is a binary. This is a heap. Actually, it satisfies the heap property. So this is how this swaps, that uh, adjusting a number to its correct position, that is done by the heapify function. So this is how the heapify works. Okay. Just repeatedly call this swapping recursively. Okay. Is it okay? Like how we are adjusting heaps using this function. Okay. Okay. So this is okay. So this is the heapify function that we have used in our last coding, and we will use it again in C++. Although you can like there is a inbuilt priority queue in C++. You can directly use that one. If you are using the priority queue, you don't have to use this heap structure explicitly. Like we are defining heaps and we are using it. If you remember Huffman code, okay, I will come to Huffman code now. But like why we are using heaps? I mean, by the way, okay. So what I was telling is that I will write this heap Huffman code again in C++, but I will implement it using heap. Okay, I will not implement the priority queue. Whereas you can use the priority queue directly. It's inbuilt in C++. You can directly call that priority queue, and you can use that priority queue to maintain the Huffman code. I mean, you can build your Huffman code. You can directly use it. There are codes, but the best way is to build the function by yourself. So that's why heap is the better option. Anyway, so what I am going to discuss now is that the Huffman code, like why we are using this Huffman code. So anybody remember like what is Huffman code, like how it works? So it's like if you have some, it's a decoding, and it's kind of encoding and then decoding of like you have to compress some data. Right? Encoding. It's a compression, right? So you have some strings or letters, whatever numbers are there, which are where the numbers are recursively like repeatedly occurring. So you take the numbers like how many frequency of a frequency of B, frequency of C, frequency of D. You take count of these frequencies. Let's say A, B, C, D. So you take count of these frequencies, and then what do you do? The task is to like assign 0, 1 binary bits to these uh, numbers such that you can minimize the number of bits that are used to represent this set of let's say this set of code, set of strings, or a set of characters. That's it. So what is the like how we are doing it? Like we are using the 0 or 1s. Yes, we are like putting the values like based on their frequencies. We are trying to put some values, and then we try to decode it from the value to this one, to this string. So this is the purpose. Uh, what this Hoffman code uses is that if you anybody remember the algorithm, or like it's completely forgotten. Do I have to recap it totally, or can I just go to the algorithm part? Anybody recall Hoffman coding, or do I have to like go through the Hoffman, the whole Hoffman coding again? I mean, like from the scratch. Difficult. It has become a theory class then. It's not a lab. Okay. Yeah, that's what I have. That's what I am saying. That uh, I can just give you the outline. It's like discussing it in details is uh, like it will take another half an hour or something like that. What I was like, if you remember, it's like no, we discussed in detail. Okay. Yeah, okay. I'll give you an overview for that. So let's say you have this set of strings. It's a string actually. So, think about this string. Hmm. So what we want is that we want to represent it using this binary code 0, 1, 0, 1. Okay. Uh, So there are two steps. First is the encoding part, and then there is a decoding. So first we will focus on the encoding part, and we want to like code it in that way such that there is no ambiguity between two numbers. Okay. So for example, like if you give A 0 and B 0 1 and C 1, then if you call 0 1, it could be AC or could be B. So which one are you talking about? It's not obvious from this type of assignment. So that's why we try to avoid this type of assignments while we are doing the encoding of this string. So for that, we use this Hoffman code, which is actually a greedy algorithm. Uh, so it's based on this frequency count. So first we count the number of frequency of each character. So there are like, I think there are 4 unique characters in here, A, B, C, and D. And if you look at the frequency of A is I think 5 times in here, and B is I think 1 time. C is I think 4, 5, 6 times in here. 6, right? 1, 2, 3, 4, 5, 6. Yeah. D is I think twice or thrice. D is twice. Okay. So these are the frequencies. So first we do is that sort them according to their frequencies. Okay. So that means that this B, D, C, A. Okay. So B has this one frequency. So 1, 2, right? Oh, AC, right? It's AC. So A is 5, B is 6. So we have sorted this one. Now, what we do is that we start with the, we will make a tree now, uh, where the leaf of the tree will correspond to every unique uh, character that we have. Okay. So if it has more character, it will have the more number of leaves. Okay. Now what we do is that we start with the minimum 2. This is where it goes greedy. We make a note. Okay. So these are the corresponding to these numbers. I don't want to get it. Okay. So here these numbers are, if you look at the minimum 2 numbers, these are 1 and 2, right? We will make a note, we will make another note, which is basically the sum of these two. Okay. Sum of these two. One is the left, another one is the right child of this node. And the value assigned in here is the, oh, sorry, it would be 3. No? So the value assigned here is 3. Okay. So this is the sum of these two frequencies. Okay. We store it in here. And what we do is that from this array where we have stored these numbers, 1, 6, we will remove 1 and 2. Just not do it here. So from this array, we will modify it to this one, 3, 5, 6. Okay. Okay. So now the next two minimum is this two. Okay. So what we do is that we add another number, another node that will take these two as their leaf, and the parent would be the sum of these two nodes. Okay. So how does it look like after this? This is 3, this is 1, this is 2. So the sum of these two nodes will be there. So that means 8, and we have 5 in here. And this 3, 5, 6 will be now changed to 8, 6. Okay. Okay. So now for the last number. So last number is 14. Okay. The sum of these two. Now, where does this 14 goes? So I have to add a note. Okay. So that would be the parent of this 8 and 6. So I'll add this node 6, add this node 14 and 8. Now from 8, there would be this subtree 5, and this is 1, this is 2. Okay. So now what we do is that we start assigning this 0 from left to right. Okay. So for left 0, right 1, left 0, right 1, left 0, right 1. Okay. So if you look at the leaf nodes, what are they? It's basically the base one, which is the smaller one, B. This one corresponding to D, this one corresponding to A, this one corresponding to probably C. So now you can see that you have these codes for every character. You have these unique codes, like for 100 C 0, D is 1001. It's like 100. Yeah, C is 101. So this is your encoding of these characters, and then you decode to using the same tree. You can also decode these numbers. Like you can take 101 and you can find out, okay, it's D. Okay, so you can traverse from the root to decode the number, and it's the same thing. Okay, so this is how this Hoffman code CDA. CDA. What is CDA? Zero. What is your question? I don't get it. I mean, that sigma tree is basically this Hoffman tree that we have discussed in here. What do you want to say? CDA 0301. I mean, are you talking about the encoding of C and DNA? And CDA 625, are you talking about? Okay. Yes. I mean, that's evident from the tree. You can easily find, you just follow from the root to the leaf. Okay. That will give you the encoding. Mm. Total beat, total beats 28. Yeah, I guess you counted the total beats of that one. Oh, yeah, maybe. Okay, it's fine. Uh, I did not count the total bit. Maybe it's 28. I have not calculated the whole numbers in there. How many were there? Oh, you just multiply with the frequency. That will give you the total bits. Uh, and you take the sum. Hmm. So it's not difficult. It's easy. Uh, so this is the algorithm that we want to target. So have you seen the heap structure in here? Okay, so that's why we need the heap structure. Okay, so that's why we were using the heap, and we will use heap when in the next class. Actually, we will do the coding for this problem. Okay, so I hope that up to now you guys are fine with this. Like why you are using heap and why how I mean how you can think about actually. You can also think about like you can observe. You have to also observe this heap structure in here. Yes, at 3 p.m. Uh, Tomorrow we will do this coding. Okay, we will start with this. There is also another thing, structure variable that I have used in the last class. I had used it before while doing the coding for um, which problem I need the notes. Uh, have we done any problem regarding this nodes and like tree-like structures? Have we done anything like that except for this Huffman coding? I forgot actually. So, oh, maybe okay, maybe not. So I think okay, then for the first time in the last class, I think I have used this structure variable. The structure is a group of variables. It allows you to like take a collection of different variables and use it in there. So and then you can access them using the structure argument, structure dot. So name dot. I mean, there are ways to define. So these structures are applicable in C++ also. So I will be using the structures again in the next class. Before doing the structures, I will discuss a little bit about the structure variable and how is it how you can implement it. And yes, so that would be sufficient. I mean, we need structures for the nodes, and using the nodes, we can define the trees that we want. And once we are able to define the trees, we can use the heap in there. And using the heap, we can also use like modify this binary tree. I mean, we can create this Hoffman tree. And in the Hoffman tree, once we create the Hoffman tree, we can also generate the codes from directly from there while traversing from the root to the leaf. So that would be the tomorrow's the outline of for tomorrow's class. So I will discuss the code tomorrow. Okay. So if you in the meantime, you guys go through this Hoffman code and also dynamic memory allocation that I have discussed today, and other things like this heap and all. You guys should go through once, and like if you have any doubt, then ask in the next class. I mean tomorrow. Okay. Okay. So that's it for today. Thank you, everyone.
So much, sir.
Thanks.